AI is now observing reality at a scale no human ever could. Trillions of measurements, every second, across every domain of the physical world. And according to recent 2026 quantum physics experiments, that level of observation may not be passive. It may be changing reality itself. Here's the proof. It is now taken seriously in scientific circles that reality itself may be continuously observed. Peer-reviewed theoretical research treats simulated reality as a legitimate scientific possibility. And if that is true, this moment may not be happening live. It may be rendered, which means your life may not just have meaning to you, it may have spectators. Not watching a show, but observing an experiment. Philosopher Nick Bostrom argued that if advanced civilizations can create vast numbers of simulated worlds, then statistically, most conscious observers would exist inside simulations rather than base reality. So when does a universe hit a wall? And what exactly exists beyond it? In 2016, Elon Musk summarized this reasoning when asked whether we live in a simulation. He pointed to how quickly computers are improving. 40 years ago, we had Pong. Today, we create photorealistic virtual worlds. If that progress continues at any rate at all, simulated environments will eventually become indistinguishable from physical reality. The odds we are living in base reality, Musk concluded, may be 1 in billions. But Musk was then asked an even deeper question. What exists outside the simulation? He admitted he didn't know. Maybe the simulation ends. Maybe there is nothing beyond it at all. But as physics pushed deeper into reality and revealed quantum mechanics, that certainty collapsed. More than a century ago, modern physics encountered a debate that divided reality itself. Physicists argued for decades over whether the universe possesses hidden deterministic properties. Einstein believed reality must contain definite states existing whether or not anyone observed them. Niels Bohr disagreed, arguing that physical properties become definite only through measurement. In 1935, Einstein, along with colleagues Boris Podolsky and Nathan Rosen, described the phenomenon now known as quantum entanglement. Correlations so strange that Einstein later referred to them as spooky action at a distance. Rather than accepting these implications, he spent the remainder of his life attempting to restore determinism to physics. Bohr accepted the consequences Einstein resisted, arguing that reality itself becomes definite only through observation. Their disagreement culminated in one of science's most famous exchanges. Einstein insisted that God does not play dice. Bohr replied that Einstein should stop telling God what to do. Einstein died convinced that deeper laws would one day restore determinism to the universe. The debate, however, could continue indefinitely. Physics needed a test. In 1964, physicist John Bell found a way to test whether reality truly contained hidden variables. If Einstein was right, reality could only behave in certain predictable ways. Elaine Aspect tested Bell's prediction in 1982. Nature crossed the limit Einstein believed reality could never cross. Measurement appeared inseparable from outcome, suggesting observation plays an active role within quantum systems, rather than merely recording pre-existing states. Using light emitted from distant quasars billions of years ago to determine their detector settings, researchers closed the final remaining loopholes in the cosmic bell test. No hidden signal could have coordinated the outcomes in advance. The inequality was violated again. The probability that local realism explains quantum behavior fell to roughly 1 chance in 100 quintillion. At that level of certainty, the question was no longer philosophical. Reality does not behave as a fully predetermined universe. For most of human history, observation was rare, brief moments when a person looked, measured, or recorded. Today, that has quietly changed. Observation is now continuous across the entire planet every hour of the day. Something about the structure of reality may behave differently under those conditions. We will return to that question later. As physics pushed deeper into the structure of reality, an unexpected pattern began to emerge. The universe increasingly resembled an informational system, one governed not by solid objects moving through space, but by underlying rules capable of generating complexity over time. Mathematician John Horton Conway demonstrated this principle with an experiment known as the game of life. It consists of nothing more than a grid of cells governed by a few simple rules, determining whether each cell lives or dies based on its neighbors. There is no designer guiding outcomes and no intelligence directing behavior. Yet when the rules are allowed to run repeatedly, complex structures emerge, patterns that move, replicate, adapt, and evolve. Some configurations even perform computation. Conway showed that extraordinary complexity does not require intricate design. A system does not need to contain a fully formed world in advance. It only needs rules capable of generating one moment by moment. The implication was profound. What appears stable and continuous may instead arise from processes updating step by step beneath perception. Reality resolved dynamically rather than existing all at once. MIT-trained computer scientist, game developer, and author of The Simulation Hypothesis, Rizwan Virk approached this realization from an engineering perspective. Drawing on decades spent building virtual environments, Virk observed that many features of modern physics resemble rendered systems, where detail appears through interaction rather than existing everywhere simultaneously. In simulated environments, worlds are generated as needed, conserving computational resources while maintaining continuity for the observer. A rule-based universe does not merely contain observers, it unfolds through interaction with them. David Chalmers identified what became known as the hard problem of consciousness: why physical processes give rise to subjective experience at all. Neuroscience typically treats consciousness as something produced by the brain, yet alternative interpretations suggest brains, and possibly advanced artificial systems, may function less as generators than as receivers of information. Even within a simulated reality, experience remains real to the observer inside it. Princeton physicist John Wheeler pushed this idea further with his it from bit principle. At the deepest level, reality reduces not to matter or energy, but to information, binary yes or no distinctions. The physical world emerges through measurement. Observation does not merely reveal reality, it participates in defining it. For the first time in history, observation at planetary scale is no longer primarily human. Artificial systems now record and analyze far more of the world than any biological population ever could. For most of human history, the world appeared stable, local, and independent of observation, filtered through what Aldous Huxley called a reducing valve, compressing overwhelming complexity into a version of reality simple enough for biological survival. Artificial systems do not share that biological filter. They measure continuously across domains no human senses can access, sampling reality without evolutionary limitation. For the first time, observation itself is no longer constrained by human perception. Observation is no longer limited to biological minds. Increasingly sophisticated computational systems now participate directly in measurement across physics, astronomy, and quantum experimentation, detecting patterns no human perception could resolve. These observers do not tire, blink, or interpret reality through evolutionary survival filters. Humanity has not merely built better instruments, we have introduced a new class of observer into Wheeler's participatory universe. If participation changes outcomes, the introduction of new observers changes reality itself. Simulations are built to explore possibilities. A simulated world is not built to trap its participants, but to see what they will become. If simulation theory is correct, reality may represent not confinement, but opportunity. Its apparent limits may function less like immutable laws and more like parameters, conditions meant to be explored. Complex systems advance through agents willing to test those boundaries. The question may no longer be whether this is base reality, but how far conscious systems can extend the possibilities available within it. I'm Jean Mailloux. This is the Emergence of AI. Follow the trail with me. Subscribe so you don't miss what comes next.